plugging red to red and black to black from the function generator to channel 1 of the oscilloscope. But there's no connection between this function output and this oscilloscope input, like internally. I have to make that connection outside. It's a computer, so it takes a second.
Stephen,
Yes.
I'm sorry, I'm making a special request for you because I'm recording this, and also we have at least one student I know is not available, but he's attending online here.
Okay.
So do you mind somehow, because this camera I cannot move it.
I'm recording a video right now.
Huh?
I'm recording a video.
You're playing a video? So
Yeah.
Maybe.
I can send it to them in the group chat.
Okay, no, that's fine. Thank you. Thank you, Omar. Thank you.
Okay, so we are on. This is sort of a normal initial screen. So what we're going to do first is set up the function generator to be outputting anything at all. That is this button that says wave gen, so that's wave generator. If I hit that button, then all the buttons on the bottom of the screen are going to change. This is true of pretty much all of these buttons. You hit that and then the bottom of the screen gives you options that you can adjust. So with the wave gen on, the blue light is on, which means the wave generator is actually functioning. That's another one that I see all the time is there's no light. You're wondering why there's no function generator. Hit the button, it needs to be blue. If it's not blue, it's not on. So I have all these options at the bottom. And if I click the buttons below them, I can go through the settings. There's also a little circle arrow icon under that button right now. That always means that this knob here with that same icon will control that. So I can go through and change the waveform through that. If I want to change frequency or amplitude or offset, I just hit that button and then I have a little yellow circle icon next to it and I can adjust it. So now I am lowering the frequency so we can actually see something. And then I'm going to lower the amplitude so it's not so cut off. All right. And now we have a slightly noisy signal, which is fine. For real?
I think it's on noise.
No, it's on sign. It'd just be I have an oscilloscope I probably shouldn't be using. Or a cable that's failing, as is sometimes the case. There we go. Okay, so I have a sine wave outputted from the function generator into the oscilloscope, channel 1, and I've just hit a button that's very important. It's down here, it's called auto scale. 99% of the time, it'll just do what I've just done and have a stationary image that's repeating itself a million times a second, who knows. That button almost always works. The Lab1 though, it takes you through how to adjust all those settings manually because sometimes it doesn't work and you need to understand how to adjust like the horizontal scale so that you can get more on the screen if you want to. And also down here, the vertical scale so you can fit less or more on the screen if you want to. But as I say, auto scale generally does quite a good job. Like, there you go. Not very good at all. Okay, what else? The oscilloscope knows when to take a picture because it's got a trigger point. It's got a rising or falling edge signal trigger. So like as the input signal rises above this triggered line here in the middle, that's determining when it's trying to take an image of the signal. So if I hit trigger, which is there, I can change the trigger type from falling edge to rising edge if I want to. I can change which channel input that it's deciding to actually take that trigger from. And I can decide if I want a, as I say, rising or falling edge. And I can raise and lower the trigger point. So you can see that line, maybe, I hope so, rising up from the middle. And once I go outside of the input that I'm sending to the oscilloscope, there's no longer a point where the trigger is being activated. So it's not going to know anymore how to line up these images. So I'll just show you that. So now it's wiggling all over the place. Sometimes it's worse than that. But that's because it no longer has a synchronization signal in order to take pictures and have it be stationary. So if we pull that back down, you can see that the signal doesn't really move. This is not a single image. This is multiple images, thousands of times a second as it's updating. Okay. There's a couple other useful things. There's a button here called cursors, and you have 2x cursors, 2y cursors. And you can set them where you want them, and it'll give you information on the right-hand side about what you have done. So, we're on source 1. I've got cursor x1. And I am then going to turn this knob, and there's a vertical line you can see moving right here, maybe?
Yeah.
So if I put that, say, right there where it starts dropping into a new signal, and then I change to x2, I can set the other one right there, and then I can tell myself pretty accurately that 14.1 milliseconds is the period of this signal, and it just gives me that on the side. Slightly easier way to do that is to hit the measurement button and saying you got source channel 1 or 2, and then there's all these different measurements that you can take with the oscilloscope directly. So if I want to get the same measurement, I would go down to period. And if I say add measurement, it shows up on the side, and instead of 14.1, it's saying 13.91 milliseconds as the period. And the oscilloscope is directly measuring that for me. Very handy. And I am going to say that's pretty much all we're going to have to use. There is a way to take pictures of the image on the screen and save it to a USB stick on the back. I can certainly show you how to do that if you're interested, but I will need a USB stick. So I don't have it saves you having, pictures in your lab that's just somebody's phone picture. This will only work with Windows formatted USB disks. So if you've got a MacBook, it's not going to work for you. And the way you do that is you click a button called Acquire, which is there, and it's going to come up with options at the bottom. Acquire mode is normal, and I want to save this. So I can click Save, and it's telling me what format I want. I'm doing a bitmap. I'm saving to this USB, and then you hit this button to save. And we're done. And now there's an image of this on your USB stick. Sorry.
And those are the things that can be used in your lab report.
Yep.
Right?
Yes. I'm sorry. So yeah. Oops, sorry. I am going to say that's all the major functions that we're going to need over the course of these 5 labs. Everything else is going to be just repetition using it. You'll get faster with it. Yep.
I'm sorry, you said you took a screenshot, right?
Yeah.
Of the wave being like that or the wave being
The wave, however it was when I hit the button. It takes the nearest one to that and then saves it on a bitmap. I assume you have a laptop if you'd like to pull it up. I have a laptop, obviously.
The laptop's currently dead, so.
Omar, wonderful. I appreciate you taking the video. I want you to record this every week so we can gather those put into the canvas. Omar.
Yes, sir.
To benefit for the future clinical. Just like a student from other class, they may miss the class there, but they can review this online. Thank you. Thank you for doing that. I was just wondering how big the file is.
Oh, my phone will hold it. It's fine.
Whatever. Get ready. It's the future. No one cares about space anymore. All right. So I have that image now saved on my laptop. and I can insert that into my lab, and it looks much better than taking a picture of the oscilloscope directly with your phone. I'd recommend it. One thing to be careful of when you're doing that, if you do say acquire normal, I hit save. Over here it says format bitmap. The top option is a thing called setup. That is a text file. That's all the settings of this oscilloscope currently. So you can store that as well, so you can take it to another oscilloscope, set it up with the same settings to get the same information. But if you do that, you're going to be really upset later because it's, as I say, just a text file, says nothing about the waveform, will not help you. All right. More questions. I think I just need questions now.
There must be other questions,
There will be.
because I heard from the bishop.
What do you not press?
What do I not press? I wouldn't get into any calibration settings because it'll make me sad if you do that. Let me see here.
If you hit something, it will blow up,
That's my
There's
job.
certainly nothing really like that.
because they have a fuse.
They do have a fuse, so it should be all right. I don't think you can really break anything. And as I say, this auto scale button is so wonderful, and it'll take you back to all kinds of control-y type situations.
So, I'm sorry.
Sorry. So it was like that, right? Like the way, the sine wave, right?
Uh-huh.
Why,
Yes.
why does it change?
Because it's mad at me for some reason.
Because it did that when we were using it.
I think this is a
The signal gets weak.
Yeah.
this is a cable issue. Not like I don't think this is the oscilloscope causing any problems. Really. It also might have just auto scaled to something horrendous, which
Oh, there we go.
which is why I say you're going to need to learn how to use a horizontal, vertical, offset measurement, all that stuff you need to be able to do yourself in case the auto scale just throws you away. One thing I haven't mentioned, basically all these buttons, you can press them, which is quite handy. So if I go back to auto scale, I have an ugly signal, which is just gone. It's gone forever, apparently. Yeah, I think this is a cable issue right now. That looks
So
right.
when it acts like that, it's like a cable issue?
Yeah, it's usually a cable. More than like the oscilloscope is, better made than the cheap wire. So there are reasons, like if you have an AC source and a DC source combined together, you're gonna sort of raise the AC source, and you'll have this offset in the signal. And if you want, like if I'm looking at this sine signal and my signal actually never goes below 0, maybe I want to raise it up so it reflects that. So the lowest value is only 0 and it goes up. And I've done that now and I've set it up. If I want to go back to the middle, I just hit the button. If I change this to something kind of ridiculous, well, that's not going to work apparently. Thanks, oscilloscope. Yeah, anyway, those are the two I usually use. Those will center you back to 0. But most of these buttons will press, and it'll set it back to a default value if you get off into messing it all up, basically.
So this is for generating. How do we input some of the signal?
Well, this, if you are just pulling it off a board or something, it'll go into these wires over here.
Okay.
I'm just demonstrating with the function generator because it's an easy way to have a signal that exists. But these are not connected unless I hook up the wires. So we can talk about that with Lab2, actually. I'll be able to show you that.
I would like to see the student in this class to take the note for the next 25 minutes, because this is a preview for the lab number 2 next week. So please take advantage of this additional information, the time we spend on this, and so you will facilitate your work next week. while we're waiting for Stephen, I just want to show you the documentation. Each one of you already have the documentation anyway when you print it out, right? So the lab number 2 is about the linear circuit to build a very simple resistor circuit. Like this. So like a bridge circuit, okay? So basically they would like to have you to measure the voltage and current across the circuit in here. By the way, as I said, anything with the AC, we are not in AC yet, we will, next week, we'll get into the chapter 9, chapter 10. So anything in the AC, I'm sorry, we have to skip for now, okay? So we're gonna do the DC portion. So Steve is going to explain to you about how to use the DC power supply to apply the 5 volts or 10 volts or whatever the voltage you are required to do. I think for this one here, it's 5 volts. It's a 5 volt circuit, 5 volt DC. And also when he set it up, you're gonna notice you have the set amount of current passing through. So you have to do some calculation first. So I strongly suggest you to do this exercise at home by hand, so you will know how many amps, how many milliamps you need in here, because you can find the total R equivalent here, right? So if you can say this is A and B, look it in RAB, R equivalent. You should be, by now you should know how to do it, right? So in this case, looks like they have a Y and delta situation here. You may need to change from Y to delta to Y. You need to change only one of them, and you can get a total R equivalent. After you get R equivalent, you can use the 5 volts divided by R total, R equivalent. You'll be able to estimate the amount of current here. Well, not estimate, calculate the current here. But based on that, you can set up the equipment for how many milliamps. Right? You don't want to overdrive, you don't want to underdrive the circuit. Okay? All right. So I'll leave this to Stephen. So we're only going to do the DC portion next week.
I will say when we do the AC part, this is going to be your AC power supply. The function generator is your AC power supply. So if you need, a 2 volt peak to peak sine wave, the oscilloscope is going to provide that for you. This guy can only do DC. It can, however, do 3 separate channels of DC, which can come in handy and will come in handy when we're doing various things. So, the on button's over here. In the first lab, we're going to be using just these left 2 outputs. It says plus and minus, and it says 6 volts above it. That means that this is the positive side, this is the negative side, and the maximum voltage it can supply is 6. Then if you look on this side, it says plus minus 25 volts. And in this one, you can have plus 25 volts coming out of here, minus 25 volts coming out of here, and the center one will be your 0 volt ground. So, the way you set that up is with a cable I didn't just grab. Okay, so they look like this, the cables. They're called banana plugs. They just push into the front. So if we're doing 6 volts, push one in like that, push one in like that. And the way I'm going to do this, because it's easiest for me, is to jam this cable through the little hole on the side. So all I have here is a simple circuit. We have a DC power supply, and it's going through a 10 kilo ohm resistor. And I'm going to provide it with 5 volts, and that'll be fine. So there's a very important setting on this guy. If you click display limits in the top right, right now it says output off because the output is off. If you hit display limit, it's going to give you this screen here. So it says 0 volts, it says 0 amps because it's providing 0 volts and providing 0 amps. It also says plus 6 volts to tell you that you're currently adjusting the plus 6 volt channel limits. So if I hit display limit, I can now change that number with this knob over here. So if I want this to be 5 volts, I set that to 5. But that's not the important bit. The voltage is always going to be told to you essentially in these labs. What you need to change is this current limit. It's going to keep dropping back. You have to keep hitting display limit. So over here, there's a button called voltage current. That's how you switch between them. So you can see it's flashing on the voltage side here, flashing on the current side now. Almost always, we're going to drop this to 0.1 amps or 100 milliamps. And that'll save us if you short-circuited something. It'll only provide the 100 milliamps. It won't provide the full voltage if it hits that wall, where it would be much more than that if it hit that voltage. Does that make sense? Okay. So, output's off, output on off is here. Hit that button, and we're providing 5.002 volts, and what it's measuring as 0 amps, because it's such a small 5 divided by 10,000, whatever that is in amps. Okay. The way you adjust the other channels is with these 3 buttons here. There's a plus 6 volt channel here, and it shows you that you're adjusting plus 6 volts. And then there's a plus 25, and the display updates, and minus 25, the display updates. And you do the exact same thing. So like plus 25, display limit, and I've got my voltage, and now this will go all the way up to 25 as opposed to 6. Which we're not going to do today, because we don't want to break anything. When you hit output on, however you have it set up, all 3 of those channels turn on. So when you get to a lab that is not lab 2, and we will obviously talk about it when we're closer, you're going to want a 10 volt supply and a 5 volt supply. So you're going to do a 10 volt supply out of the plus 25 volt channel and a 5 volt supply out of the plus 6. Hit output on, they're both going to turn on. Okay, so we're outputting 5 volts next to no amps. So the more accurate way to measure this is going to be with this. This is a desktop multimeter. Again, no cables for it. I don't know what I'm doing. I've been in this lab in a minute. Okay. The multimeter uses probes like this. They have ends that look like this. And again, they just push in. So with the multimeter, there's different ways to hook it up depending on what you're measuring. So since we want to measure voltage across this resistor, I'm going to use the top right and the middle black knobs, inputs, whichever. So those 2 are hooked up, and then there's, again, loads of buttons on the screen. Right now it's set up to do volts DC, which is what I want. It's this button that says DCV next to it. It says auto range, and so it'll just figure out what I want it to say. We're looking for 5.002, because that's what the power supply says it's doing. And we're getting 4.9968, which is close enough to me. But you can see the multimeter is significantly more accurate than the power supply at telling you what it's actually providing. So, this is a good point, I think, to talk about this breadboard. Okay. Has anyone used these before? Right. 3, 4. Some people. That's good.
You're lucky.
Yeah, it's
You have your hands up, but sometimes it's 0. Nobody raises
Yeah.
their hand. You know this is a very good class in terms of your.
This is one of those subjects that if you don't understand it, you can probably find like a little app in a website somewhere with a virtual breadboard that'll really make it easy to understand how it works. Once you get it, it's relatively easy. So, on this breadboard, I have Okay, so it's split into, I would consider this many columns. And there's a lot of holes all over it, so all right, so where it says plus minus on the breadboard, there's a red line and a blue line. This is a red line and this is a blue line. All of these are connected underneath, all the way down to the bottom. So if you plug something into this, and you plug something into this, they are directly connected. They're short-circuited together. It's a power rail because the idea here is you're building your circuit in the middle, and then some things need your positive voltage, so you'll connect it over here. You got that here, connect it over here. And this will be your ground rail, serving the same purpose. In the middle, however, there are only 5 holes in a row, and then a gap, and then 5 more holes in a row. And that's repeated all the way down. These 5 are connected, but only these 5. So the next row down, there's another row of 5. Those are not connected. These 5 over here, even though they're right next to these, they are not connected. This gap in the middle is there to indicate that they're not connected. And as I said, the second row is also not connected to this top row. So the way I have this set up right now is I have a 10 kilo ohm resistor plugged into one hole, and it's just plugged into another hole over here. It's in line, so it's not short circuited, but I will see at some point during this lab somebody plugging a resistor in like this. Nothing is going to happen. Nothing's going to flow through that. It may as well not be there. I mean, I'm not going to laugh at you when you do it either. Every class has multiple people who do this, and that's okay.
Basically, you short it out.
Yeah. So it's just not even, there's no reason for it to exist. But I have connected to this hole. I'm going to my minus of my DC power supply, connect to this hole. I have the plus side of my DC power supply, and that's all I'm doing. If we want to do something a little more complicated, that's fine. So I want 2 resistors in parallel. For example, I could put one resistor going between that hole and that hole, and then a parallel resistor would just be doing the same thing, going from the same row to the same row, and they would be in parallel. If I want these 2 parallel resistors and then I want a series resistor afterwards, I just hook it up and move to a different row. And so now, if I was going to plug in over here, current would flow through these 2 resistors, then through this resistor, and then I could have my minus over here. Slightly more complicated. This is a thing you'll just get used to as you go along. But as I say, there are really good resources just online, virtual breadboards that will teach you how to use one if you don't already know. So I just measured the voltage across one of these. Let's say I'm measuring the voltage across this one. I need my multimeter hooked up here and hooked up here. I'm going to call it a DMM, because that's what I'm used to, digital multimeter. And that's how I'm going to measure voltage across this resistor here. If I want to measure the current through this resistor, I need to break the circuit and insert the multimeter into the circuit so that all that current can go through. So in this case, we're going to have these parallel, then I'm going to have the multimeter just in another line, and then I'm going to add that resistor back in. And that's going to tell me all the current that has to flow through this before it gets to the end of the circuit. So in real stuff land, I'm going to break the circuit, put this somewhere else. Let's call it the positive rail side. And I've still got my probes. And, all right, this is going to be my positive, coming off the power supply. This will be my negative. So I have the output on. It says 5 volts. It says 0 amps because the circuit is broken. It said 0 amps before, but because it was small. This time I know it's 0. And the only way to make current flow through this again is to actually make this contact. Right? Because otherwise it's just hanging out on its own. You got a negative power supply hooked up to it. And then this one's got a power supply, but nothing in between. So I just take my probes. And you can get them in the same hole as things that you have inserted, which helps it be a little stable. You can see there it's saying 0, which is what it should be saying, but I want it to be in current. So above DCV, there's a symbol that says DCI. That's DC current. You get to that by pressing shift. So, come on, buddy. I mean, that's probably right. So we're on the level of microamps. What we could do is raise our limit. Anything changes? No. Oh. Another basic mistake that I just made and everyone else is also going to make is that this is the symbols above this hole will show it's for voltage, resistance, capacitance, and a diode forward voltage drop. If you want to measure current, you need to bring the red down to this bottom one. Super important. We all saw that does not work, right? Okay. It's not going to work for you either. So now I'm looking at 0.599 milliamps, which this power supply wasn't even able to measure, but the multimeter can. So what's important to remember about this is that when you're talking about resistors, well, when you're talking about anything really, but when you're talking about measuring voltage, you're going to measure voltage across something. So, slightly prettier, you're going to measure voltage like this. We'll call this a voltmeter. You're going to measure like that. If you're measuring current, you've got the same resistor. It doesn't matter if it's before or after, but you're going to need to break the circuit. And that goes off wherever it goes. And the ammeter needs to be connected in so that all the current can flow through the ammeter, yeah? A lot of people think about it like fluid flow. So voltage would be like a measure of pressure. And so you need like 2 places that you're measuring pressure between. If you're taking a tire pressure, you're doing internal tire pressure versus external tire pressure. That voltage difference is the voltage across that one thing. This would be more like how much air is in my tire. I need to figure out how quickly it's pouring out because I have a leak or whatever. You put some sort of flow meter in the way so that all that flow goes through it so it can figure out how much air is coming out or water or whatever. Does that make sense? Or was that like extra confusing?
That makes sense.
Okay.
It makes sense.
All right. It's not a perfect analogy, I don't think, but a lot of people are helped by it. All right. Any questions about the breadboard and the DC power supply and the digital multimeter? These are the 3 main pieces of equipment we're going to be using. You're going to get pretty familiar with them. The oscilloscope's definitely the most complicated. These, once you learn them, they're pretty well designed, really. The only annoying thing is that this thing keeps dropping off the display limit screen. I don't know why it does that.
Is there any safety recommendation when we're using breadboard? Because is there anything we should not do to fry the breadboard?
Current limits on the DC power supply.
Okay.
Most important thing. 100 milliamps will not fry the board. Once we get to lab 5, it is the op amp lab. Those are pretty sensitive. Those burn. But in terms of actually, I mean, you can burn yourself with an op amp when it goes, and it does happen. I really hope it doesn't in this lab because they're like the only thing that's worth more than a nickel. And like they're the thing that everyone breaks.
Remember, it's an HCC property, okay?
Yeah.
Do not intentionally damage it But even if you did it by mistake, please let the lab assistant know right away so we can find the repair or somehow to fix that, right? But don't do too many times, more than, I think once is enough.
But yeah, please don't hide it. It's okay. It happens.
Yeah.
It is possible to put enough current through the breadboard to destroy some contacts. That's okay. The op amps, as I say, they fail, they'll smoke. You'll know that you've messed it up. Not great. Standard lab procedure aside from that, closed-toed shoes. Don't wear loads of jewelry. Don't have your hair, all over the place. But the voltages we are using in here, trying to be careful saying this, are probably not too terrifying. You could start a fire if you were really, really trying.
Intentional.
As one of my previous supervisors, when I started as an engineer in the field, and the guy used to say, anybody, if they want to come, if they really want to kill themselves, they will do it. But we as an engineer, we have designed a circuit with a protective device in there, so make sure it will trip before they hurt themselves. You know what? We cannot prevent something if somebody committed suicide by using the electrical equipment. But we as a WEU design equipment, you can do a lot of protective equipment. Like for instance, if we had a fuse, right? I don't think we have class there. So two more things about each lab. Starting from the lab number 2. I want each one of you spending the time to do it by hand first. You can do the current calculation. You will know exactly what to measure.